All right, so we're moving ahead to 11.1. The reason that we're skipping from 9.4 to 11.1 is not because chapter 10 is unimportant, we'll come back to it, but because they're somewhat connected. So this is on quadratic residues and non-residues. And so this section, I'll put this in the intro, is briefly sort of connected to the idea of solving congruences, certain types of congruences. So for an intro, basically in chapter 9 we solved things like, so for example, say 3x to the fourth is congruent to 7 mod 20 using indices. So in this section we want to look at a much more specific question. So here we'll look at the following. Over here, let's say we'll ask the question, what are the perfect squares mod a prime? So for example, something like mod 7, what are the perfect squares? And so we could work this out by simply squaring everything, right? So we could do, say, square everything. So we could say, for example, 0 squared is 0. This is all mod 7. 1 squared is 1. 2 squared is 4. 3 squared is 9, but that's 2. 4 squared is 16. But that's also 2. 5 squared is 25. That's also 4. And 6 squared is 36. That's also 1. So we could say maybe, and this is a big maybe because we're going to adjust this all a bit, that 0, 1, 2, and 4 are the perfect squares. We'll actually end up deleting 0 for various reasons, but for just as a cursory glance, and then we could say that 3 and 5 and 6 are not. So in each case, right, like what we're doing here is we're solving essentially x squared is congruent to a mod 7, and we're asking for which a is there a solution. Maybe even more than one solution. So this is the problem we're tackling. So this is similar to solving equations. I mean, it is solving equations, but it's a very specific example when we're looking for perfect squares. And so it turns out this isn't really obvious. So it's easy enough to square everything, right? But that could get hard when the primes are big. So it's easy to get a hold of perfect squares. For example, you could say like, well, I could just, even if the prime is huge, I could take a number, I can square it, I can get something that's a perfect cube, a perfect square. But reversing that process is much harder, right? If I'm given something and I want to know if it's a perfect square, that's significantly harder. And problems like this, problems where one direction is easier, in this case, squaring something is easy, but the other direction, figuring out if something is a square, is harder. Processes like that lead to encryption methods in number theory. Almost, there are a very large number of problems like this for which there are cryptographic protocols associated to these. So this is another reason why we're bringing this up, even though we won't look at that specific cryptographic protocol. This is just a good introduction to sort of see the underlying mathematics. So what we'll do next is we'll define all the definitions associated, and we'll do some counting. That'll be the first part. So this is when we get into number 2. So this is quadratic residues. And non-residues. And we'll say definition and counting. So the definition will actually give initially not for a prime. We'll give it in general, but then everything else in this section will focus on for primes, because that's where sort of the notation turns out to be good and things like that. So we'll say if m is a modulus, this is in a positive integer. And we'll say a is an integer, and we're going to make this integer relatively prime to m. Some books don't necessarily do this. However, if you don't do it, it leads to all sorts of special cases in places, and you sort of have to be much more careful. So if we keep things relatively prime, which our book does and most books do, it keeps things nice and tidy. So then we say that A is a quadratic residue and we can either say mod or of m. Both terms are used. So this is if x squared is congruent to a mod m has a solution. In other words, if it is a perfect square, then we say it's a quadratic residue. We pull at that. And then we'll say that a is a quadratic non-residue. Mod slash of whichever term you want, m, if x squared is congruent to a mod m, has no solution. Now notice that both of these are only applied to things that are co-prime to m. This should be GCD equals 1 up here. So if your A is not co-prime to m, you wouldn't use either of these. You wouldn't say it's a quadratic residue. You wouldn't say it's a quadratic non-residue. That's the first thing. Second thing, keep in mind that we don't say it's not a quadratic residue. It's sort of a weird nomenclature. We say it's a quadratic residue or it's a quadratic non-residue. But the phrase it's not a quadratic residue is not really used. So for example, just to reflect upon what we did over here, we would throw away 0 because it's not co-prime to 7, and we would say in this case that 1, 2, 4 are quadratic residues. I'm going to abbreviate this quadratic residues mod 7, and 3, 5, and 6 are quadratic non-residues mod 7. And we can find those out, of course, just by squaring things. Just not the most efficient way, but it gets the job done. So the first thing you might notice, and the first thing we'll prove here, is that in this specific example, the quadratic residues 1, 2, and 4, those each have 2 solutions. Right? So if you reflect back, let me circle some things. In order to get 1, we can square 1, and we can square 6. And when we get 4, we can square 2, or we can square 5. And when we get 2, we can square 3, or we can square 4. And you might see why that is immediately. You may or may not, and that's okay. And then for the other ones, the things that are not quadratic residues, 3, 5, 6, of course we get nothing. So in other words, we can say that every target either has 2 solutions or no solutions, right? 1, 4, and 2 have 2 solutions. 3, 5, and 6 have no solutions. So we notice that for this example. Whether that's true in general is what the theorem says. So the theorem will be very specific now. So everything we'll do for the rest of this section will be for primes, and specifically will be for odd primes. There's of course only one even prime, and that's 2, and it's sort of a bit of a headache in a lot of proofs. So very often it's excluded. So we'll say if P is an odd prime, and we'll say that A is an integer with P not dividing A, So this means, this tells us in this case the GCD of A and P is 1. So we're in the good category of things that we're interested in. And we can see that x squared is congruent to A mod P. So this either has no solutions or two incongruent solutions mod P. So no solutions or two incongruent solutions mod P. So like on our example, 4 has two solutions, 5 has no solutions. So the proof of this is pretty straightforward. So let's take a look. So for the proof, so what we'll do is we'll show that if you have one solution, then you have another, which is different, and that you can't have more than two, basically. So we'll start by saying, look, if there are none, then we're done. Obviously, right? So then what we'll say is, suppose you have one solution, right? So if x is a solution to x squared is congruent to A mod P, then the claim is that negative x is also a solution. But more than that, negative x is a different solution. So to see this, to see that it's a solution is obvious, right? Because note that if you square negative x, you get the same thing as when you square x, and therefore you get A mod P. And so everything is good. But we need to make sure it's different, right? So to see that x is different than negative x mod P, and think about what would happen if it were the same. To see that they're different. If they were congruent, right, so then what we would have is if you add an x to both sides, you'd have 2x is congruent to 0 mod P. So that would tell us that P divides 2x. And since P is a prime, this is where this is kicking in. P divides 2, or P divides x. But P cannot divide 2 because it's a prime greater than 2. Greater than or equal to 3. So this would tell us that P must divide x. But this is a problem because look, x squared is congruent to A mod P. So what this means if P divided x, it would divide x squared. So let me write this out. So if P divides x, then P divides x squared. So P divides, so x squared is congruent to A mod P. So A is x squared plus a multiple of P. So P would divide A plus a multiple of P. For some z, for k and some z, but then because P divides kp, P divides A. But we said that P doesn't. That was a hypothesis. So what that ascertains is that establishes that this is not true. X is incongruent to negative x. So we definitely have two solutions. So then we say to ourselves, so what if there are more than two? So we could approach this maybe by saying, like, what if there were three? But we're actually going to be a bit sneakier. What we'll do is we'll show that any two must be either the same or negatives. And that way, if you had three of them, they would have to pair up as two of them being the same. Right? So we'll say this. Well, suppose that, say, in the notes I used x1 and x2. So think of these as any two solutions. Right? So then what we get is x1 squared is congruent to A, which is congruent to x2 squared. because they're both solutions. So that says that P divides x1 squared minus x2 squared, if you delete the a from the middle and subtract. Right? So this tells us that P divides x1 minus x2 times x1 plus x2. So it divides one of those, because when a prime divides a product, it divides one. And those would give us that the first would be the same as x1 is congruent to x2 mod p, or x1 is congruent to negative x2 mod p. So what this means is if you have 2, they must be negatives. So if you had 3, they would have to pair into negatives in some way that 2 would be the same. Right? So in other words, to be more succinct, thus the only possibilities are negatives. And that's the QED. Now, it's less relevant how many solutions there are than what this tells us about how many quadratic residues there are. Right? So before I erase anything, just consider what this means is if x squared equals a, it has 2 solutions or no solutions, then for each a, the x's pair up. They either pair up or there are none of them. So what this means is if you look at just the x's that you're squaring, each pair of them gives you a quadratic residue, which means out of all the p's, if you're excluding 0, then half of the remaining ones will be quadratic residues and half will not. Right, so let me clarify that a bit more in the theorem. So this could be a corollary, but I'm going to give it a theorem because that way it sort of carries a bit more weight. So we'll say if p is an odd prime, so then there are exactly p minus 1 over 2 quadratic residues and p minus 1 over 2 quadratic non-residues mod p. So the proof is pretty obvious. What we're going to do is we're going to square all of these guys. These are all the things between 1 and p minus 1 that are coprime, or really between 0 and p minus 1 that are coprime, which is 1 through p minus 1. So if we square each of those, each result will occur twice. By the previous theorem. So what that means is that since each result occurs twice, there could those 1 through p minus 1, right? We only get half of those as results. So thus will be this. There will be p minus 1 over 2 quadratic residues, and the ones we don't get, like you say, the non-results. Will be the quadratic non-residues. And so that's the end of that. So what that means is, for example, if p equals, say, 29, there are 29 minus 1 over 2, which is 14 quadratic residues, and 14 quadratic non-residues. So this is simply a counting statement. Like, it just tells you, like, hey, how many there are. They subdivide half and half, basically, other than 0, and that's that. Now, the other thing we can make, this isn't really a counting argument, but it's the other theorem that I'll give before we have some new notation, is a sort of a comparison statement about when you have a quadratic residue, which makes it sound like I'm simplifying the process, but I'm sort of giving something that's equivalently difficult, and you'll see what I mean in a second. So we'll say that let p be an odd prime, and let r, this is just going to connect it to the previous section that we looked at. let R be a primitive root mod P. Now we didn't cover this particular section, this is in 9.2, which we skipped, but it's a fact that primes have primitive roots, so it's guaranteed. So then for any A, with P not dividing A, we have A is a quadratic residue of P if and only if the index base R of A is even. So this is sort of a comparison statement, and so it doesn't necessarily make it easier, because we mentioned in 9.1 and 9.4 that finding indices is difficult. So we have this sort of parallel difficult problem, right? Determining if something is a quadratic residue is difficult. Determining the index is difficult. So this doesn't make finding quadratic residues any easier. It's just a different way of thinking about it. So the proof of this is fairly quick, so let's just do that. So here's the proof, nice and quick. So two directions to show. We'll do the backwards one first, not that it matters. So if the index is even, then just one observation. So take a look. If I take R, if I take half of that index, that's an integer. So if I take R to that power, whatever that value is, and square it, I will get R to the index base R of A, and that by definition is A. It's like a logarithm. So the index base R of A is saying, what power do I raise R to get A? Then I raise R to that power, I get A. And so here we go. So A is a quadratic residue mod P. So that way is done. For the backward direction, what I'm going to suppose that A is a quadratic residue. So what that means is there exists an X such that X squared is congruent to A mod P. So then what I'm going to do is I can take the index of both sides, basically specifically the index base R of both. So what we get is this. Now remember, when we take the index of both sides, the modulus changes to phi of the modulus. So this becomes phi of P, but phi of P we know is P minus 1. Right? So for a prime number, that's what it is, right? So what this tells us is that, now there's one last step we could do. Let's be careful that we can pull down the 2. This is mod P minus 1. So this tells us that the index base R of A, this is 2 times the index base R of X plus some multiple of P minus 1. Now if you look at all this, this bit right here is even. P is odd, so P minus 1 is even. So this whole thing is even. And that's the end. So again, not saying that makes it any easier to calculate when something's a quadratic residue, but it gives you sort of a parallel way of looking at it. So what we've done so far is we've looked at what it means to be a quadratic residue. Basically think perfect square. We've talked about how many of each there are, basically how many perfect squares mod P, how many non-perfect squares mod P. We're excluding 0. And we're just looking up to congruence, so we only need to look at 1 to P minus 1. And then we have this sort of comparison between indices and quadratic residues. So next thing we're going to do is we're going to introduce some notation for this and look at some nice things that come out of the notation. So 3, this is what's called the Legendre symbol and properties. So what we're going to introduce is just introduce a symbol which has a value associated to it, which tells us if something is a quadratic residue or not. and then look at ways to combine these, which help us sort of give an algebraic way of working with whether things are quadratic residues or not. So the first thing is the notation. So we'll say if P is an odd prime, and P does not divide A is an integer. I'm not going to worry about saying that right now. So we define the Legendre symbol. So the symbol is parentheses A over P. Right? So before I give you the definition, a couple important things I'll write in a second. Don't forget the parentheses. This isn't a fraction, and so it's just a notation, so it needs the parentheses. They're an essential part of the notation. If you don't have them, you'll read it as a fraction. Now it looks like a fraction, so you sort of just have to understand what you mean. The context will always be clear for us, because in number theory we're very rarely working with fractions in a real sense. So but don't forget the parentheses, and it's not a fraction. So we'll define that this is plus 1 if A is a quadratic residue. I don't need the plus, of course, but I'll put it for now. Mod P, and negative 1 if A is a quadratic non-residue. Mod P. Now I will, though, use the terms numerator and denominator just because I need something to refer to these, but the warning here is it's not a fraction. In the sense of, like, you know, a ratio kind of a thing, but we will say numerator and denominator just because it makes it handy. Like, you could say top and bottom as well, but this is so we have some phrasing that we're comfortable with. So for example, we saw from before that 1 and 2 and 4 are quadratic residues mod 7. So I would write this. And 3 and 5 and 6 were not. So we would write this. And these are because 1, 2, 4 are quadratic residues, and this is because 3, 5, and 6 are quadratic non-residues. So, few properties of this, or a few things that go with it. Right? So first theorem is maybe the biggest one. This is Euler's criterion. Euler seemed to have done everything. So Euler's criterion says the following. It says P is an odd prime, and P does not divide A is an integer again. So it tells us that the following is true, that A over P is A to the P minus 1 over 2 mod P. Really, this is a congruence. Let me be accurate. So notice this also is a different way of telling if something is a quadratic residue, right? Because the left-hand side will be 1 when it's a quadratic residue. The right-hand side will be 1 when it's a quadratic residue. Now, the right-hand side may still be difficult to calculate, right? Raising things to powers and reducing them mod P can be a difficult thing to do. When you're reducing mod P, you're dividing, so this can be hard to calculate in a real-world setting. So let's go through the proof for this. The proof is not particularly hard, and it's sort of fun because it goes over some things that we've looked at before. So it's a really good proof to work through. So the way that we'll prove this is we'll basically say, like, we'll look at two cases. We'll look at the case when A over P is 1, and then we'll show that A to the P minus 1 divided by 2 must be 1 mod P as well. And then we'll do the same for negative 1. Right? So in other words, we'll say suppose that this equals 1. So what we're doing is we're claiming that A to the P minus 1 over 2 is congruent to 1 mod P. That way we know they're the same. So when this is equal to 1, right, this implies that there exists an x, right? Because for this to be 1 means it's a quadratic residue. So there exists an x such that x squared is congruent to a mod p. So if that's the case, then also notice that if you take a to the p minus 1 over 2, that this is x squared to the p minus 1 over 2, because a is the same as x squared. Then the 2's cancel in the sense that we get x to the p minus 1, and x to the p minus 1 is congruent to 1 mod p. And this is by Fermat's little theorem. And that's it, right? In the sense that thus a over p is congruent to a to the p minus 1 over 2 mod p, because they're both 1. In fact, one of them is equal to 1, and one of them is congruent to 1. Therefore, they're both congruent to 1. So on the other hand, suppose that a over p is equal to negative 1. And now I am claiming that a to the p minus 1 over 2 is congruent to negative 1 mod p. So this is actually a little sneakier. So what I'm going to do is I'm going to look at each of these, each x in the set 1, 2, up to p minus 1. So for each of these, we know each such x has a unique y also in that set, let me make my little parentheses right, satisfying xy is congruent to a mod p. Now, take a second to digest why this is. This is a linear congruence right here. The coefficient is x, and we know that a linear congruence has a solution if the GCD of the coefficient and the thing we're setting it equal, or the coefficient and the modulus divides the a. So this is because this is a linear congruence. The GCD of the coefficient and the modulus is 1. And this is because x is between 1 and p minus 1. So the GCD of x and p is 1. Right? And this divides a. So this means there exists a unique solution mod p. And that's the y. Right? So in general, remember that this was the situation. So this has solutions if and only if the GCD of A and M divides B. And the GCD is how many solutions it has. So in this case, it's the GCD of X and P, which is 1, that divides A, so there's one solution. So I know there's one solution. There's a Y for each X, such that when I multiply them, I get A. Now the other thing to notice is that the y that we get is not the same as the x. In other words, everybody has something which is different from it. And this is because, these are different, because if y were congruent to x mod p, then a would be xy, which would be xx, which would be x squared mod p. But a is not a quadratic residue, or a is a quadratic non-residue, because a over p is negative 1. Right? So therefore I know it's quadratic non-residue, and so x squared is congruent to a, has no solutions. Right? So what we get here is these values, if we look at all of them, these pair off into pairs that form a product of A. This is a minus in there, that went kind of bad. Right? These pair off into pairs which multiply to give A. And there are p minus 1 over 2 such pairs. Right, so what this tells us is if I multiply them, what we get is we get A to the p minus 1 over 2 mod p. But if you remember Wilson's theorem, states that that left-hand side is congruent to negative 1 mod p. So that tells us that A to the p minus 1 over 2 is congruent to negative 1 mod p. So that tells us that A over p, which is equal to negative 1, is congruent to A to the p minus 1 over 2 mod p, QED. And again, it doesn't make things easier to do, but just to finish on an example here, you'll see why. Right? If you look at 6 over 11, right? This is congruent to, according to the theorem, 6 to the 11 minus 1 over 2, which is 6 to the 5. That's big. I mean, it's not huge, but in the grand scheme of things, these numbers get big fast. This is congruent to 10, which is congruent to minus 1 mod 11. So 6 is a quadratic non-residue mod 11. It is not a perfect square mod 11. So what we'll look at next is we'll look at a theorem that sort of gives us some properties of the Legendre symbol that allow us to do some calculations that sort of help us see when things are and are not quadratic residues a little more easily. So what I'm going to do is I'm going to clear the screen here and give the next theorem, give the proof of it, give a lemma that follows, do an example, etc. So this is C. This is a theorem, which I'll say properties. This is properties of the Legendre symbol. So we'll say if P is an odd prime, and A and B are integers with P not dividing A and P not dividing B. So we have all of the following. So I. So if A is congruent to B mod P, I'll prove all these, but I'll make some comments as we go. Then A over P equals B over P. Now this should be fairly obvious in the sense that if A is a perfect square, then B is a perfect square because they're the same mod P. But the thing to keep in mind about this is, the way to think about this is you can reduce the numerator mod the denominator. When we're calculating. So 2 is sort of the really nice one, is we have AB over P equal to A over P, B over P. So we can break up the numerator across multiplication. And 3 is fairly obvious, which is, because it follows immediately from 2, is that if you have a perfect square, then you simply get 1. So the proof of this, 2 is the only bit that really takes any work. 1 is fairly clear. If, say, oh, let me put this as an if and only if. We can say this is clear. In the notes I thought of it the following way. This is clear because x squared is congruent to A mod P if and only if x squared is congruent to B mod P, when A and B are congruent mod P. So 2 follows immediately from Euler's criterion, which is why we did it first. So the thing to observe here is that if you look at a b over p, by Euler's criterion, this is congruent to a b to the p minus 1 over 2. And this splits up. This is just product of exponents, or properties of products with exponents. And this is then congruent to a over p, b over p, mod p. Now, you might think we're done, but the statement that we actually gave up here is that the things are equal. The statement that we've got so far is that congruent mod p. So there are a couple different ways. You might see that it's fairly clear at this point that they're the same, but we get a little more technical about this. So we need, just to clarify the issue, we need equal, not just congruent mod p. So the way to see this really, really formally, we'll say, well, since p is greater than or equal to 3, and since we have this congruent, right, the congruence back down over here is this congruence, this tells us that p divides the difference. But that difference, because each of those, right, this expression, each of those individual ones, let me actually write it this way. This is either plus or minus 1. Each of these is either plus or minus 1. Which means this product is plus or minus 1. Which means when you subtract these, this could either be positive 2, if you had, say, a positive 1 minus a minus 1, could be a 0, or could be a negative 2. So you have a p that's greater than or equal to 3 dividing one of these. This can only happen if that difference is 0. If this thing right here equals 0. That's the only way that you'll get 3 dividing it, right? So thus that equals 0. This guy right here. And then we're done, because they must be equal. And then 3, of course, follows immediately from 2. Oh, that should be a 2. So here's an example of how this can be useful. And this is a bit abstract, but that's okay. But suppose we were to say if p, we'll do a more concrete example later on. If p is an odd prime, a is a quadratic residue, b is a quadratic non-residue, then ab is a quadratic non-residue. And this is because ab over p is a over p, b over p. A over p is 1 because it is a quadratic residue, and b over p is negative 1 because it's not. It's a quadratic non-residue, and therefore the product is negative 1. So this sort of gives you this insight as to how all these things go together to give you various possibilities. So the last thing I want to do before some special cases, which I'm actually going to put in a separate video just to keep things brief, is just give Gauss's lemma, which is another way of calculating the Legendre symbol, which I'm not going to prove. I'm just going to give an example. I'll mention as to why I'm not going to prove it in a second. But here's what Gauss's lemma says. All right, so D, Gauss's lemma. So let me give this to you, make a few comments about it, and then just do an example. So suppose P is an odd prime, and P does not divide A is an integer. So we'll say let S will be the number of least positive residues of this set A to A, 3A up to and including p minus 1 over 2a mod p, which are greater than p over 2, then a over p equals negative 1 to the s. Now, let me make two notes about this. One is the proof. I'm going to omit this. The proof is fairly lengthy. And the only reason I'm really giving it is because there's one place in the future that we'll use it, so I want to have it handy. But I will make a note, this is not at all obvious, right? Like, when you read this, at least for me, there's no intuitive reason why this is clear. Oh. It's not at all obvious why this is the case. But let's just do one example, just to see that it gets the job done. So consider p equals 13 with a equals 8. So we have p minus 1 over 2 is 6. So take a look at, so I'm going to examine all of these. Okay, so these guys, a, 2a, up through 6a. So these are multiples of 8. Which I'm going to reduce mod p, mod 13. So this becomes 8, 3, 11, 6, 1, 9. This is mod 13. And if you count those and ask this question, how many are greater than p over 2? So p over 2 in this case is 6.5. So if you look at which ones those are, I'll just label them. 8 is greater than 6.5, so is 11, so is 9. There are 3 of those that satisfy the criteria. So S equals 3. Thus, in this case, 8 over 13 is negative 1 to the 3, which is negative 1. So at the end, 8 is a quadratic non-residue. And again, just to make sure we're contextualizing all this, this means that x squared is equivalent to 8 mod 13 has no solution. So again, not at all obvious, right? Like, we shouldn't look at this and see that this makes sense. And this is why the proof is fairly lengthy, because it sort of digs in deep as to what's going on here. So this is almost the end of this section. I'm going to stop here because we're already about 50 minutes and I'm trying to keep these videos not crazy long. So there's two special cases we need to look at. And so I'll do them in a separate video. Actually, now that I say that, I'm saying that and I'm thinking like it's going to be about 5 minutes. So let me add them to this. So the last thing I want to look at is 2 special cases of this. So let me clear the screen, do the special cases, and then we're done with the section. And it's not clear probably yet and why these special cases are useful. So these are them specifically. But the reason I want to go through these is because we're going to next hit a topic called quadratic reciprocity. And so using quadratic reciprocity along with the rules that we've learned makes it easy for us to do some calculations about quadratic residues. So the first theorem is this, is when is minus 1 a quadratic residue mod p. In other words, when is minus 1 a perfect square? So the theorem says the following, that this is, you get 1, in other words, it's a quadratic residue if p is congruent to 1 mod 4, and it's negative 1 if p is congruent to 3 mod 4. P has to be one of those if it's odd. So the proof is fairly nice. So by Euler's criterion, we have negative 1 over p is negative 1 to the p minus 1 over 2. mod p. And so in the first case, right, if p is congruent to 1 mod 4, then p is 4k plus 1 for some integer. So you can see where this is going now. If I plug that in, we get 4k plus 1 over, or 4k plus 1 minus 1 over 2. The minuses cancel. I get 4k over 2, which is 2k. And this is 1. And then if p is congruent to 3 mod 4, and p is 4k plus 3, so minus 1 over p is minus 1 to the 4k plus 3 minus 1 over 2 mod p, which is negative 1. So now we'll get a 4k plus 2, which when I divide by 2 is 2k plus 1. That's odd. That is what congruence is. Let's be clear. This is negative 1 mod p. So that's really, really nice. Now, just for a simple example, what that tells you is, say, if you want to do minus 1 over, say, 13, right? All you do is you say, like, well, you look at the 13 and you go, well, 13, this is a multiple of 4 plus 1, right? This is congruent to 1 mod 4. So this is 1. Whereas, for example, something like, say, negative 1 mod over 15. So 15 is congruent to 3 mod 4. So this is negative 1. So negative 1 is a quadratic residue. Or if you prefer, 12 is a quadratic residue. It is a perfect square. Whereas negative 1, this is mod 13 over here. Negative 1 is a quadratic non-residue, mod 15. If you prefer, 14 is a quadratic non-residue, mod 15. Not a perfect square, mod 15. But 12 is a perfect square, mod 13. Or negative 1 if you want to think about it in both cases. And so then the other one I want to give, this one I won't prove because it's fairly lengthy, which is theorem when is negative 2 a quadratic residue, mod p. And it turns out that 2 over p, again, two cases. 1, if p is congruent to 1 or 7, mod 8, and negative 1 if p is congruent to 3 or 5 mod 8. The proof I'll omit because long. And just a little note here that this is the same as saying 2 over p is negative 1 to the p squared minus 1 over 8. So it turns out that if you sort of categorize this the way we did the previous ones, that if you say, for example, p is 8k plus 1, and you put that into the right-hand side down here, that you'll get a positive 1. So this is fairly easy to prove. You can try it if you want. It's pretty much like the calculation we just did for a negative 1. So an example here would be, say, if you were looking at, let's phrase this as a question, say, is 2 a quadratic residue mod, say, 23. And you go, well, 23, that's a multiple of 8 plus, right? Like 24 is a multiple of 8. That's sort of too big. 16 is a multiple of 8. So plus 7, so this is congruent to 7 mod 8. So 2 over 23 is 1. So yes, it is. And again, you can think about that as it's a perfect square. You can think about it as, if you prefer, x squared is congruent to 2 mod 23 has a solution. Doesn't tell us what it is, but it tells that it has one. So that's the end of that section, and there we go.